So we are going to talk about an important theorem in vector calculus called Stokes Theorem, the Curl Theorem, or the Kelvin-Stokes Theorem. All three of those names mean the same thing. And in order to understand that theorem, we're going to need this definition of the curl of f dotted with a normal vector. If you haven't seen this definition before, I have a video explaining curl that uses this definition, so you can check the link in the description for that. Now, in order to understand the curl theorem, we're going to start with a closed line integral of f dot dr. But we're going to do a little bit of setup with the curve of this line integral in order to get to our final theorem. We're first going to start with a surface that has some boundary. For example, if we have a cylinder as our surface, then the boundary is the two circles on the top and bottom of the surface. It's where the surface has an edge, where it ends. So we're going to have a surface, which we'll call S, and the curve over which we're going to integrate is the boundary of that surface, which in this case ends up being two separate curves. So we're looking at some arbitrary surface, and we're choosing our curve to be the boundary of that surface. Now remember that we're doing a line integral of a vector field, so it matters which direction we move along our curve. In this case, we're going to say that we move along the curve counterclockwise. Now we're going to do an important step. We are going to split this line integral up into two different parts. And the way that we'll do that is by splitting the surface into two separate regions. So we've split our surface into two smaller surfaces, and now we have two different boundary curves, which are the boundaries of those two surfaces. Just like before, those are closed curves, and what we want to look at is the sum of the line integral of our vector field over each of these curves after we split up the surface. Well, notice that when we do these two line integrals together, they're still going to include the boundary of the original surface. They're still going to have that original curve going all the way around. It's just going to be split between them. But when we add them together, we'll get our original result back. Let's look at the extra part that's added when we split up the surface, which is what's in the middle. This part of the curve was not originally there. But remember that all of these line integrals are oriented counterclockwise. So for surface 1, the curve is going to be going upward in the middle because that's the direction of counterclockwise. But for surface 2, if we move counterclockwise, in the middle, the curve is going to be going down. What that means is that f dot dr, that depends on the direction that we're moving along the curve. If we move the opposite direction, this dot product becomes the negative of our original answer. So in the middle, these two curves share the same boundary, but they're moving in the opposite direction. So one is going to be the negative of the other. We're integrating over the same vector field, so these two are going to cancel out. The middle is going to cancel to 0, and the only thing that's left is the integral over the original boundary, which means that when we add these two line integrals together, we get our original answer back. Now, because splitting up the surface gave us the same answer when we added these two line integrals together, we can repeat this process again. We could split surface 1 into two more separate surfaces, and we'd still get the same answer. In fact, we could split it an arbitrary amount of times, getting arbitrarily small surfaces, but when we add them all together at the end, it's still going to be the same line integral. So let's consider an arbitrary sum of these surfaces. So we're taking the line integral over the curves of f dot dr, and we're going to add those together for an arbitrary amount of surfaces. We've split up the surface into a bunch of parts. Now the reason that I've used a double summation here instead of just a single summation is that this is starting to look a lot like a Riemann sum for a double integral. We're taking the sum of a particular value that depends on the point we're at, and we're summing that value up over a two-dimensional region, a surface. And we're able to keep making the area of those regions smaller and smaller and smaller. Since we're looking at areas, that would be a double integral as our input range. So we have a double summation here. Now, in order to make it a Riemann sum, we would want to multiply by the area of that region. That's what the Riemann sum is. Because when we're looking at a Riemann sum, we take the value at each point in the region, and then we also multiply by the area of that region. In this case, since we're looking at the area of a surface, I'm going to call it ds, for an area of the small part of that surface. Now, in order to maintain the original value, if we multiply by ds, we're also going to need to divide by ds. And now this looks a lot more like a Riemann sum. We're taking the sum over a two-dimensional region of a value evaluated at a point times the area of that region. So now if we want to go from a Riemann sum to an integral, we want to take the limit as these regions get smaller and smaller and smaller towards 0. Let's see what that would look like. Because we're integrating over a surface, we're going to get a surface integral. But what is going to go in here? Well, remember that we're taking the limit as the area approaches 0. And this expression looks very familiar. 1 over the area times the closed line integral of f dot dr. That's exactly what we have in here. And we're taking the limit as the area approaches 0. So if ds gets smaller and smaller and smaller, this is going to approach what we have on the left side here. It's the definition of the curl of our vector field f dotted with n. And so this Riemann sum, as ds approaches 0, is going to turn into this surface integral. The important thing to recognize now is that at every step we took here, we preserved the original value of the line integral. Every time we split up the region into smaller regions, we get the same answer. And even if we take an infinite number of regions as we decrease the area down, down, down to 0, every time we split it, we keep the same answer. So this is still equal to the original line integral over the curve of f dot dr. And this is the curl theorem. So because of the definition of curl, this surface integral of the curl of f dot n is really talking about a bunch of line integrals on top of the surface. But when we put two line integrals next to each other, in the middle, they point in opposite directions, which means that they cancel out, and the only thing that remains is the integral over the boundary. Now there's one more element of the curl theorem that we're going to go over. When we use the curl theorem, most of the time, we start with the surface integral of curl of f dot n, and we go from there to the line integral, because it often simplifies things to go down a dimension. But when we do that, we have to make sure that we choose the right orientation for our curve. Now the way that we do that is using a variation of the right-hand rule. The way that this works is, let's say we have a surface like this, where the boundary, in this case we're looking at a hemisphere, the boundary is the circle on the bottom, and say the normal vector points out. The way that we use the right-hand rule is we point our right thumb in the direction of that normal vector, and we move it until we're at the boundary of the surface. From there, we want to curl our fingers until they point parallel to the curve. The direction that our fingers are pointing, that is the direction the curve has to move. In this case, when we're at the very edge of the surface right here and the normal vector is pointing straight to the right, our fingers are going to point into the board, which means that the orientation of the curve goes in this direction. Now there's actually a really cool visualization of this that I'm going to put on the screen right now. So here we're looking at an example of an arbitrary surface with two different boundary curves, where the normal vector points outward. In order to think about the right-hand rule, we visualize our right hand as a spinning gear where our thumb points in the direction of that normal vector. The direction that that gear is spinning is the same as the direction that your fingers will curl when your thumb points in the direction of the normal vector. So if you think about bringing that spinning gear down to the boundary of the curve, the direction that it spins on that edge of the curve, that is the orientation that we want for the curve. Now the reason that we use that particular version of the right-hand rule comes from the definition of curl. Curl is originally defined in terms of this line integral. So when we're looking at the boundary, we want our line integral around the boundary to match the direction of the curl line integral. But when we define curl, we define that the direction of the curve C always follows that right-hand rule that we just talked about. And that's why when we're looking at the boundary, the curl theorem also has to follow that same rule. So now we're going to go through one example of where the curl theorem can be useful. We're going to evaluate the surface integral of curl of f dot n ds, where our vector field f is given by x plus y minus x plus 3, e to the x squared plus y minus z. And S is the surface defined by x squared plus y squared plus z squared equals 1 for z greater than or equal to 0. And we have an outward pointing normal vector. Now first we need to look at the surface over which we're integrating. We have x squared plus y squared plus z squared equals 1. We know that that defines a sphere. But because z is greater than or equal to 0, we're looking at the top half of a sphere. So this is a hemisphere. Also notice that the inside of this surface integral is the curl of f dot n ds, which is exactly the inside that we need in order to use the curl theorem. So in this case, we just need to figure out what is the boundary curve. Well, when we're looking at a hemisphere, the boundary is going to be this bottom circle, the circle in the xy plane. So we can define that, but first we need to think about the orientation of this curve. And just like we were looking at a second ago, if we think about an outward pointing normal vector, at the edge our fingers are going to point into the board, so the curve is going to move in this direction. We could also think about on the other side, if the normal vector points outward, it's going to point this way, and then when we curl our fingers parallel to the curve, it's going to point outward. So again, we have our curve going in the same direction. If we think about looking at this from the top, this is actually a curve that's moving counterclockwise, which is the direction that we're used to curves moving. If we looked at it in the xy plane, this is going to be a circle of radius 1 that looks like this, and the orientation is going to be in this direction. If we want to parameterize this, it's going to be pretty simple. R of t equals, well, for the x and y value on a circle, we want cosine t for the x value, sine t for the y value, and at the boundary, z is going to be 0. And this works for us because cosine and sine start at 0 and move counterclockwise around the circle. So now we've defined the curve that we can use for our line integral, and we also know that t is going to go between 0 and 2 pi because we're going all the way around the circle. Now we need to find f dot dr. We know that dr is just r prime of t times dt, so what we're really looking for is f dotted with r prime of t. So let's plug in, first of all, these coordinates for r of t into our function f. Now we want to dot that with the derivative of this vector with respect to t. Well, the derivative of each of these parts with respect to t, derivative of cosine is negative sine t, derivative of sine t is cosine t, and of course the derivative of 0 is still 0. So when we do this dot product, after we multiply each part and expand everything out, we're going to get this expression right here. We have a minus sine t cosine t and plus sine t cosine t that are going to cancel. And also notice that even though our original vector field had a super weird z component that would probably be very difficult to do with a surface integral, once we do this dot product, that completely disappears. We're just going to get a 0 right there. So all we have left is minus sine squared t minus cosine squared t, which is going to be a minus 1, and then 3 cosine t. So this is what we're going to plug into our integral. That means that our surface integral of curl f dot n ds over a hemisphere just simplifies to the integral from 0 to 2 pi of 3 cosine t minus 1 dt. And the result for this is negative 2 pi. And that's how we use the curl theorem to do surface integrals. So that is the curl theorem, also known as Stokes theorem. It talks about the surface integral of the curl of f dot n, but because the curl is defined in terms of a line integral, when we do the entire surface, all that we get is the line integral over the boundary. And this identity is super useful when we want to calculate those surface integrals. you.